Welcome to this introduction to photonics. Today, we are exploring the technology that quietly powers our modern world. Even though we don't usually think about it, light is at the core of how we communicate, how we process information, and even how we explore science. So, in this presentation, we are going to break down how light works and why it's so important in today's technology. So, what exactly is photonics? At its simplest level, photonics is the science of light, but in practice, it's much more than that. It's what allows us to generate light, control it, and detect it in very precise ways. This is incredibly important because modern communication systems rely on light to transmit data over long distances at extremely high speeds, basically at the speed of light. Instead of sending electrical signals through copper wires, we use light signals in optical fibers, and the particles that carry this light are called photons. So whenever you stream a video, send a message, or browse the internet, photonics is working behind the scenes to make that possible. Light is fascinating because it doesn't behave in just one way. It actually has three different personalities, depending on how we look at it. First, we have the ray model. This is the simplest way to think about light. It assumes that light travels in straight lines, which helps us to understand reflection and basic propagation. This is a model we use when dealing with mirrors and simple optical paths. Second, there is a wave model. In this case, light behaves like a wave, similar to ripples in water. This allows us to explain more complex phenomena like interference, diffraction, and polarization. These effects are essential in many optical technologies. And finally, there's the particle model, where light is made up of tiny packets of energy called photons. This model explains quantum-level interactions like how light can transfer energy to electrons in the photoelectric effect. So, overall, light is both a wave and a particle, and that dual nature is one of the most important ideas in modern physics. Light is actually just a small part of a much larger range of electromagnetic waves. This range is called the electromagnetic spectrum. On one end, we have the radio waves and microwaves. These are low energy and long wavelengths, which makes them ideal for communication technologies like radio, television, and wireless signals. On the other end, we have X-rays and gamma rays. These have very high energy and extremely short wavelengths, which is why they are used in medical imaging and scientific research. Right in the middle is the visible spectrum, which is the only part of the spectrum that human eyes can detect. What's interesting is that this visible band is actually very small compared to the entire spectrum. In photonics, we often use wavelengths outside the visible range, specifically infrared, because they are more efficient for communication through optical fibers. To really understand how we control light, we need to look at the three fundamental behaviors. First, reflection. This is when light hits the surface and bounces off it. The angle at which it hits the surface is equal to the angle at which it reflects. This is why mirrors work the way they do. Second, refraction. This happens when light moves from one material to another, like from air into water, and changes direction. This bending happens because the speed of light changes in different materials. And third, diffraction. This is when light spreads out after passing through a small opening or around an obstacle. Diffraction becomes specifically important when dealing with very small scales or precise optical systems. Together, these three behaviors form the foundation of optics. So, why does refraction actually happen? The key idea here is that light doesn't travel at the same speed in every material. In vacuum, light travels at its maximum speed, but when it enters another material like glass or water, it slows down. This change in speed causes the light to bend. We describe this effect using something called refractive index, or N. It's defined as the speed of light in vacuum divided by the speed of light in the material. So, the higher the refractive index, the slower the light travels in the material, and the more it bends. This concept is essentially for designing lenses, optical systems, and fiber optics. Light doesn't just travel, it also carries energy. We can calculate the energy of light using the formula of E equals h times nu. This tells us the energy of a photon depends on its frequency. Now, here's something interesting. Even a very small amount of light contains an enormous number of photons. For example, a 1 watt light source at a wavelength of 1 micrometer produces around 5 times 10 to the power of 18 photons per second. That's a massive number, and it shows how powerful light can be even at a relative low power levels. Even though those numbers are huge, communication systems are incredibly efficient. In real-world data transmissions, we don't need billions of photons per signal. We can work with surprisingly small amounts. For example, a receiver detecting just 1 microwatt of power at 10 gigabits per second might only receive around 500 photons per pulse, and that's enough to reliably transmit data. This is one of the reasons photonics is so powerful. It allows us to send huge amounts of information using very little energy. One of the most important concepts in photonics, especially for fiber optics, is the total internal reflection, or TIR. When light travels from a denser material to a less dense one, it bends away from the normal. But if the angle is large enough, beyond what we call the critical angle, something interesting happens. Instead of passing through the boundary, the light completely reflects back inside the material. This means that none of the light escapes, it's 100% reflected. This principle is what allows us to trap light inside fiber optics. Using total internal reflection, we can build structures called waveguides. A waveguide essentially traps light and forces it to follow a specific path. This path doesn't have to be straight. It can be curved, twisted, and bent, and the light will still stay inside. For this to work properly, the material inside the waveguide must have a higher refractive index than the material outside. This difference keeps the light confined and guided along the desired path. An optical fiber is one of the most common types of waveguides. It has 3 main layers: the core, which is the central region where the light travels; the cladding, which surrounds the core and has a slightly lower refractive index. This difference ensures that the light stays trapped inside through total internal reflection. And finally, the coating, which provides mechanical protection and keeps the fiber from being damaged. This principle allows light to travel over very long distances with minimal loss. While optical fibers are widely used, they are not the only way to guide light. We can also transmit light through open air using free space optics. This involves using devices like lenses and mirrors to direct and focus light beams. Free space optics are useful for applications like long-distance communications, imaging systems, and even satellite links. In some cases, they allow us to send data without needing physical cables. In real systems, light signals are not perfect. As they travel through the medium, they experience 2 major effects: attenuation and dispersion. Attenuation is a gradual loss of signal strength. This happens because some of the light is absorbed by the material and some of it is scattered in different directions. Dispersion, on the other hand, affects the shape of the signal. Instead of staying as a sharp pulse, the light spreads out over time. There are 2 main types of dispersion. Intermodal dispersion. It happens when different light paths or modes take different amount of time to travel through the medium. Intramodal or chromatic dispersion happens because different wavelengths travel at different speeds. Over long distances, these effects can cause pulses to overlap, making it harder to distinguish between bits of data. Total attenuation combines all sources of signal loss. We measure it in decibels per kilometer. as the distance increases, the signal power decreases. Usually, it's an exponential way. This is why repeaters or amplifiers often needed in long-distance communications to boost the signal. In multimode fibers, intermodal dispersion can become a serious limitation because different modes travel at different speeds. The different signal spreads out quickly. Step signal fibers are simple but only effective in short distances. Graded index fiber improve the performance by smoothing the path differences, making them suitable for medium distances. But for long distance, high-speed communication, the best solution is single-mode fiber, which allows only one path of light to travel. Even with single-mode fibers, dispersion doesn't completely disappear. Intramodal or chromatic dispersion still occurs because the refractive index of the material changes slightly with wavelength. This means different colors or wavelengths of light travel at slightly different speeds, which can still cause signal spreading over long distances. Another important factor is scattering. Scattering occurs when light interacts with small imperfections or variations in the material. Instead of continuing in a straight path, some of the light is redirected in different directions. This reduces the strength of the signal and contributes to attenuation. There are two main types of scattering. Rayleigh scattering depends strongly on wavelength. Shorter wavelengths scatter much more than the longer ones. This is actually why the sky appears blue. Mie scattering, on the other hand, affects all wavelengths more evenly, which is why clouds look white. Both types of scattering are important when analyzing signal loss in optical systems. So, how are all these concepts used in the real world? Photonics plays a major role in advanced security and defense systems. Fiber optic sensors can be used for border monitoring and protecting critical infrastructure. With technologies like distributed acoustic sensing, a single fiber cable can act like a massive sensor, detecting vibrations and potential threats over long distances. In naval applications, fiber optic systems can be used for submarine detection and underwater monitoring. And for communication, technologies like free space optics and quantum key distributions allows to transmit that data securely, even through the air. Looking ahead, photonics is shaping the future of technology. It promises faster communication, more efficient energy systems, and virtually unlimited bandwidth. If the 20th century was defined by electronics, the 21st century is being defined by photonics. The future truly belongs to the photon. Thanks for watching.